Hi everyone, welcome to my YouTube channel, and in this video we will look at problem 639 from Leetcode. This is the second problem in this Decode Way series. This one is a little bit difficult, but if you cannot solve this on your own, that's okay. You can watch this video and you can learn how to solve this problem after. So here is the problem statement. I want you guys to pause this video for a second. Try to come up with your ways to solve this problem. If not, you can just write down how to approach this kind of problem. Let's look at my solution. So the strategy for solving this kind of problem is that we will be using dynamic programming, and I'll be using bottom up. Bottom up is much simpler to explain and easier for other people to understand. So we will be creating one-dimensional DP array because we only have to consider one state when we are moving from one transition to the next transition, right? We have to consider only one state. But that doesn't make this problem easy. This problem is hard because you have to consider like bunch of cases. Like the recurrence relationship in this problem is quite huge, but don't let that scare you. So, and then our DP of J will be defined as this way. So the total number of ways we can decode a string from 0 all the way to j minus 1. And in Python, we have s of colon and we have j here. This means we are considering a string from 0 all the way to j minus 1. So the difficult part is how the recurrence relationship works in this problem. And so yeah, let's see the solution for this. So initialization. Well, so dp of 0, we set that equal to 1. Okay, so that's this part. And then now we are looking at dp of 1. So dp of 1 means we are looking at s of 0. And we have 3 cases to consider. Well, actually 4 cases, but well, the first case is 0. When this is 0, then that's the good choice, good thing for us. Then we don't have to compute like this. We don't have to run, for loop, computing all this, filling out dp array. So if the first element is 0, we just return 0 and we exit this for loop. We don't have to carry out the for loop. We just return 0 immediately, right? Because when this is 0, then this is the in value, right? We cannot have 0, 2, even though when you write like int of 0, 2, you get 2, but 0, 2 is not valid, right? So that's the lucky case. And when the first element is this asterisk mark, that means we have 9 choices to consider, right? 1 through 9. So that's why we have 9 here. And when we have 1 or 2, then we have 1. So that's the initialization here. Now for case 1, when we have, say, when we are at here and we want to compute, say, dp of 4, right? dp of 4. But then we have 2 cases to consider. So when the previous element is this asterisk mark, when this is equal to 1, 2, or 0. So something like that. So probably more than 2, I think. But for this case, when the previous element is asterisk mark, then our recurrence relationship will be dp of I equals 2 times dp of I minus 2. Now this is the key. We are not looking at I minus 1, but I minus 2, right? Because why do you think that's the case? Well, because we have this one is 0, right? We cannot have 0 itself. So we have to look at the previous element as like single entity. So we have, in this case, we will be looking at, say, so the only case we would have is this one will be 1 or 2, right? Then this becomes 10 or 20. So if you look at this example, right, this is 4 because how many choices do we have? How many ways can we decode this? Well, we have 1 through 10, 13, 10, 1 through 20, 13, 20. Notice that the last element here, it is 10 or 20, right? We don't have 1 or 0. That's why we are looking at dp of I minus 2. Okay? And not dp of I minus 1. So for this slide, I think the way I explain this may be a little bit confusing, but towards like in the next coming slide, I think I have much better presentation to explain what's going on. So just bear with me, okay? So the next one is, we are still on case 1. The next case is when the previous element is either 1 or 2. Now in that case, our recurrence relationship will be dp of I equals dp of I minus 2, right? Why is that? Why is that the case? Well, if you look at, say, if you look at this example, how many ways can we decode this 1310? How many ways can we decode this? We have two cases, right? We have 1, 3, 10 or 13 and 10. And notice that here we are adding 10 only, right? And then we cannot have 1, 0 because 0 itself cannot be a valid number. So we are looking at dp of I minus 2. We are not looking at dp of I minus 1. That's one of the hardest part about this problem. And so that's why dp of I minus 2, how many ways can we decode this? Like 1, 3 or 13, right? Here we have 1, 3 and 13. And then for this case, when we are at here, so dp of say 4, now we'll be just adding 10, right? But then notice that this doesn't change the number of ways we can decode this, right? We just add 10 to this existing set here, right? So we still have 2 ways of decode this. So that's why we have equal sign here. dp of I equals dp of I minus 2. Now we have to consider, now we are moving on to the case 2. Case 2 is a little bit difficult because when we are say at here and then we have an asterisk mark and then the previous element is also asterisk mark. Now in that case, the recurrence relationship is given by dp of I equals 9 times dp of I minus 1 plus 15 times dp of I minus 2. For this big case 2, we have 4 sub cases to consider. So we have when the previous element is also asterisk mark, when this pink one is 1, 2, or it can be others, right? 3, 4, 5, 6, 7, and 9. So when we have asterisk mark for this one and then same for this one, then the recurrence relationship is given by this. Why is that? So yeah, I think this part is much cleaner than this one, but I think once you understand this part, the case 1 will be very simple. So let's look at this. Now we will be looking at, so here let's look at this part first. Why we have 9 times dp of I minus 1. So for this one, okay, for dp of 3, what do we have? We can have 131, 132, 133, all the way to 139, right? And then we have 13 and 1, 13 and 2, all the way to 13 and 9. So that's why we have 18. dp of 3 is 18 right here. And then for this one, so for dp of I, we will be adding, so asterisk mark, we can have 1 through 9. So we'll be adding 1 through 9 here. So for each case, for each of these, we'll be creating 9 more cases, right? 1311, 1312, all the way to 1319. So that's why we multiply this by 9. Same for here, 13 and 9, we can write it as 13 and 9 and 1, 13 and 9 and 2, 13, 9 and 8, all the way to 13, 9 and 9. So we have 9 cases to consider. That is why we have dp of I equals 9 times dp of I minus 1. Now that's not the end. We also have to look at the dp of I minus 2. So that will be this one. That's for dp of I minus 2. Now if you look at this same example, dp of 2, we have 2 cases, right? 1 and 3, or this one should be 13, I'm sorry. So this one should be 13. So we have 1 and 3 and 13. Now for this 1 and 3, we have 11, 12, all the way to 19, 21, 26, right? Notice that we, asterisk mark, we do not include 0. So we have 11, 12, all the way to 19, 21, all the way to 26. And how many of them are there? We have 15. So that's why we are multiplying 15, because for 1 and 3, we'll be creating 15 more of this. And then for 13, we'll be doing the same thing. So 13, 11, 13, 12, all the way to 13, 26. So that's why we have dp of I equals 9 times dp of I minus 1 plus 15 times dp of I minus 2 when we have this case, right? And then the next case, there will be, we are at case 2 when the previous element is 1. Now in that case, we have this recurrence relationship. 1, 3, 1, 13 and 1. That's for DP of 3, okay? And then for each, we'll be adding 1 through 9. So that's why we have 9 here. And then for DP of 2, we'll have 1 and 1 and 3 and 13. Now for each of these, 1 and 3, we'll be adding what? 11 all the way to 19. We cannot have like 21 because notice that this one is fixed, right? This one is fixed, so we have 9 of them. Same for 13, we will be having 13 and 11, 13 and 12, all the way to 13 and 19. So we have 9. So that handles this case. So we have dp of I equals 9 times dp of I minus 1 here, plus 9 times dp of I minus 2. That's for this part. Now we are on case 3. And so when this is equal to 2, this is slightly different because we have 2 here. So the dp of 3 is the same. We can add 1 through 9. That's why we have like 9 times here. But then for the dp of I minus 2, we have 6, right? We have 21 all the way to 26. So that's why we multiply by 6, not 9. So that's the only difference from this guy. And then we have the case of when it is none of the above, say it will be 3, 4, 5, 6 all the way to 9, right? In that case, we'll be just looking at the previous case, so there will be dp of 3. And then, so in that case, we will have 1, 3, 3, 13 and 3, right? And then for each of this, we'll be adding 1 through 9, right? So for 1, 3, 3, we have 1, 3, 3, 1 all the way to 1, 3, 3, 9. That's why we have times 9 here. Same for this guy. 13 and 3, we have 13 and 3 and 1 all the way to 13 and 3 and 9. So that's another 9 times here. Okay, so now we have case 3. So we have big case 3, and then we have 4 subcases to consider. So this part is other than 0 or asterisk mark. Let's just say we have 6. Now if this is 6, then we have this case. So we are on case 1. When the previous case is asterisk mark, that means what is our dp in this case? If like this number is less than or equal to 6, then our recurrence relationship is given by dp of I equals dp of I minus 1 plus dp of I minus 2 times 2. Now if that's not the case, then we have dp of I minus 1 plus dp of I minus 2. Now what do I mean by that? Let's look at the case when this is valid. So let's just say 6 here, because this second case is actually very simple. So I will talk about the first one. So let's assume that we have 6 here. Then we have dp of 1. What is our dp of 3? dp of 3 in this case will be 1, 3, 1 all the way to 1, 3, 9. And then we have 13 and 1 all the way to 13 and 9, right? And then now because we have 6 here, well, we are just adding 6 to existing all this combination, right? Here, 1, 3, 1 and 6, 1, 3, 9 and 6, right? We are just adding 6 to these guys. So we are not exactly increasing all those valid possible combinations. We are just using the existing combination and we just add 6 to all those sets. So that's why dp of I minus 1, we don't have any multiplication going on. But then for the previous case, so dp of 2, now we have 1 and 3 and 13. Now for this each case, we can have, because we have an asterisk mark here, we can have 1 or 2. So in other words, we can have 16 or 26, right? So that's what's going on here. And then same for here, we can have 1 and 6 or I'm sorry, I made a mistake here. Okay, now for this part, so for dp of 2, we have 1 and 3 and 13, right? But for 1 and 3, we have 16 or 26. That's why we have we'll be creating two two valid combinations here. So from 1 and 3 we had 1, but then we'll be creating another one. So we have 1 and 3 and 16, 1, 3 and 26. For 13 we have 13 and 16, 13 and 26. So that's why we have 2 in front of this dp of I minus 2. So I hope that makes sense. And then we'll be looking at this one. So our case 2 will be when this number is 1, then the recurrence relationship is given by dp of I equals dp of I minus 1 plus dp of I minus 2. Okay, so dp of 3, we would have 1, 3, 1, 13 and 1. And then we will be just adding 6 here. So we do not change. So we are just adding 6 to existing combination here. Same for dp of 2. We'll be just adding 16 to this guy, right? So that's why our recurrence relationship is given by dp of I equals dp of I minus 1 plus dp of I minus 2. Case 3, I mean, this one is exactly the same with this one. This one. So I will leave that as an exercise for you. Very simple. And then for the last case is just dp of I equals dp of I minus 1. I know this one was a lot to think about, all those subcases and cases, right? So if you look at my code, this is how my code looks like. I know it looks very verbose, but I think this one is, at least to me, something that anyone can come up with. This is the initialization step, and then we'll be running our for loop from 2 to n plus 1. Well, not including n plus 1. So, and then this one is our case 1. This is our case 2, and this is our case 3. Now for each case we have sub cases to consider. Here we have 2 sub cases. Here we have 4 sub cases. Here we have 4 sub cases, right? And then we return the last element in our DP. So that's for this problem. And let's look at the code. Okay, so let's run this code and see what we get. Okay, so that's for this problem. Well, if my video helps you guys understanding this problem, please give me a thumbs up and subscribe to my channel. And I'll see you next time. Bye-bye.